Right, so first thing that we're going to talk about today is going to be oxygen transport. So oxygen is transported, 99.9% of oxygen basically is transported by red blood cells. A very, very small amount of oxygen is transported in the plasma, but we're going to kind of ignore that, okay? So inside the red blood cells, there is a protein called hemoglobin. Okay, we already mentioned that before. So hemoglobin consists of 4 units, 4 subunits, individual proteins, 2 alphas, alpha subunits, and 2 beta subunits. Okay, each protein, each hemoglobin, each alpha globin and beta globin, which each subunit contains organic molecule called heme. Okay, inside of each heme there is an atom of iron. Okay, so each atom of iron can bind a single oxygen molecule. Does that make sense so far?
Can you summarize that a little bit?
Yeah, so 4 protein subunits form a molecule of hemoglobin. Okay? Usually the acronym for it is HB. Each subunit binds one molecule, one organic molecule of heme, HEME. Within that organic molecule there's an iron atom. This iron can bind oxygen. So one hemoglobin molecule can bind maximum 4 oxygens. Does that make sense? Now the reaction of binding is usually can be written 2 ways. One, you can write it down this: hemoglobin plus oxygen. Okay, you can write it this. Or another way, sometimes how it is written, they add deoxy hemoglobin on the left plus oxygen results in oxy hemoglobin. So essentially deoxyhemoglobin is the one that does not have oxygen bound to it, and oxyhemoglobin is the one that does. Does that make sense so far? Good? Okay. Now, very important feature of oxygen binding to hemoglobin is so-called cooperative binding. In cooperative binding, next oxygen binds easier than the previous one. So for instance, first oxygen, binds not readily, so to say. Am I clear? But once you got number 1 bound, second one binds better. The third one binds even better. And the fourth one binds very easy. So this is the cooperative binding. Does it make sense or not?
Are you talking like up there? So that first one?
Here. So, well, it doesn't matter. There's no like a number, but imagine you have bare hemoglobin molecule. You have a deoxyhemoglobin that doesn't have any oxygens there, okay? So you try to slap the first one, and it's the hardest part, so to say. Once you got first one bound, second one binds with ease. Third one binds with more ease, and fourth one is the easiest one to bind. We clear? Now, this process, sometimes is called loading. But the obvious question is, what's going on during unloading? What's going on? So this process, loading of hemoglobin, obviously, happens in lungs. Does that make sense? This is where oxygen binds. Now, unloading happens in tissues. This is when hemoglobin and oxygen complex, the oxyhemoglobin, dissociates into hemoglobin and oxygen. And this oxygen goes into tissues. Does that make sense? So to explain how it works, we need to look at so-called hemoglobin dissociation curve. Okay? Good so far? To understand what's going on here, the y-axis on this graph will be hemoglobin saturation. So what is hemoglobin saturation? Look at this molecule right here. This molecule has 4 spots for oxygen. Does that make sense? These spots can all be free. There can be only 1 spot occupied by oxygen. It can be 2, it can be 3, or 4. If hemoglobin does not bind any oxygen, then the saturation is 0. If a molecule of hemoglobin binds only 1 out of 4 possible oxygens, the saturation will be 25%. Makes sense, right? 2 out of 4 possible are bound means 50%. 3 out of 4 possible, 75, and if all 4 oxygens are bound to hemoglobin, the saturation is 100%.
We need, like, well, one of those questions we on the test, like, what's the percentage?
No, I'm not going to ask you to calculate percentage. It's not math class, right? You can divide 3 by 4, obviously, but I explain this so that there's another aspect to it. At any given moment, there are hemoglobin molecules in the blood that are fully saturated, 100%, right? Some 75% saturated, some 50, and some 25. When you average those saturations across the board, okay, all hemoglobin molecules in the entire blood, that gives you an average saturation which can be, I don't know, 93 or 98 or 72, because we take an average. Does that make sense? Okay, awesome. Now what is on the x-axis? On the x-axis is the partial pressure of oxygen. Essentially, if you think about it, the concentration of oxygen. Okay? It's basically the same as concentration. So keeping that in mind, let's take a look at the shape of the curve first. So what I want you to understand very, very clearly, look, this is not some law of physics that you can deduce mathematically. This hemoglobin dissociation curve was measured. Am I clear? It was measured by scientists, okay? So the common question is why? There's no why. It is what it is. So let's take a look what's going on at the partial pressure of oxygen around 100. Okay. So this is going to be 100 millimeters of mercury, okay? See that? So this partial pressure, I mean, I'm not really a good artist, as you can see, but the saturation is around 100%. So what does that mean? Now look, where is the partial pressure of oxygen the highest? In the lungs, right? In the lungs. This is where oxygen is, like, this is where you have most oxygen, in the lungs. Am I clear? Right? So this color of a marker means lungs. Partial pressure of oxygen is 100 millimeters of mercury. Okay? And hemoglobin saturation, almost 100%. Does that make sense to you? So it means that practically every spot here is occupied by oxygen. Good? Now, why this is important? Look what happens when you start moving from 100% to, say, I don't know, 90%. Is saturation decreasing? Yes, it is decreasing. Is it decreasing by a lot? No. So what does that mean? If you travel into the mountains, okay, like you go to Colorado, like 14,000 feet elevation, okay, the concentration of oxygen in the air will go down. Are you following me? Which means the partial pressure of oxygen in your lungs will go down from, say, 100 to 95. Will it affect the saturation of hemoglobin? Yes, a little. You're still going to have a considerable number of hemoglobin molecules carrying a lot of oxygen. Does that make sense? Now let's take a look what's going on in the tissue. So as you know, in the tissue, you don't have to memorize these numbers. In the tissue, the partial pressure, well, it's not great. I have to remove it. In the tissue, the partial pressure of oxygen is about 40. Okay. Now look at this. Okay. So what is the saturation of hemoglobin at this partial pressure? 75%. It's not precise. Huh?
Oh, I agree.
Okay, now, look, why this is important. Let's take a look. So when your blood, now listen closely, when your hemoglobin is in the lungs, all spots are occupied. Am I clear? When your hemoglobin is in the tissues, how many spots are occupied?
3?
Only 3 out of 4. Does that make sense? What does that mean? That means that 1 out of 4 oxygens went into the tissue. Am I clear? Hang on a second. If you say, no, I don't understand, hang on a second. So this difference between 100% saturation and 75% saturation goes into tissue. Now, think about it in terms of analogy. Look, okay. Imagine that you have a truck. Hemoglobin is your truck. Are you with me? It gets loaded in the lungs all the way to the top. We're good? It gets to the construction site, whatever. tissue. It does not unload everything. It unloads just a quarter. Am I clear? And it goes back into the lungs. Does that make sense? This may sound counterintuitive until you start thinking about metabolically active tissue. So imagine you playing soccer, right? Okay, imagine you're playing soccer. You're running very intensely, right? So your muscles work, metabolize very, very intensely as well. You good so far? So in order to metabolize, they use a lot of oxygen. Use up a lot of oxygen. Make sense? So suddenly, the concentration of oxygen, the partial pressure of oxygen in your muscle tissue isn't 40, but let's say 20. Okay? So this is going to be your metabolically active tissue. I mean, it's not correct. The difference, it's notoriously off. Okay? It should be somewhere like here. Okay? So metabolically active tissue. Suddenly the do you understand why the partial pressure of oxygen in metabolically active tissue starts to get lower? Your muscles use a lot of oxygen. Does that make sense? They spend a lot. And this is why the concentration of oxygen in your muscles drops. Am I clear?
So because you're using a lot of oxygen, it's making...
Doesn't make, just uses it. You have $40 regularly in your pocket. Then you use $20 for a meal. Now you have 20, right? So usually your muscles have 40 millimeters of mercury concentration of oxygen. When they start working really hard and they start use oxygen for metabolism, the partial pressure drops to 20 because they just use it up. Does that make sense? Look what happens to hemoglobin at 20. At 20, hemoglobin saturation at 20 millimeters of mercury becomes, I don't know, I don't remember really. Let's say it's 40%. So what does that mean? It means that now you have not 25, not the quarter unloaded, but 60% unloaded. Does that make sense? Can you excuse me for a second? So let's summarize. Look at this. When hemoglobin in the blood is in the lungs, where partial pressure of oxygen is 100, it is 100% saturated. When it gets into the tissues, where partial pressure is 40, it becomes 75% saturated. So the difference, 25%, goes into the tissues. Are you following so far? However, if your tissues are very metabolically active and use a lot of oxygen, the partial pressure of oxygen in those metabolically active tissues will be 20 millimeters of mercury. Are you following me? Which means that the saturation of hemoglobin at that partial pressure will be, say, 40%. Okay? Which means now the overall amount of oxygen that will go from hemoglobin into tissues will be not 25% of the original load, but 60%, which exactly makes sense because these tissues constantly use oxygen and they need more oxygen constantly. Is that clear? Does it make sense? So basically, think about it in some other terms. I'm going to give you some stuff here. Look, almost flat line of hemoglobin dissociation curve here on top means that this is adaptation to altitude. When you go into the mountains, does that make sense? You go into the mountains. This is how you adapt to the decrease in oxygen concentration in the mountain air. Rapid change in unloading in this part of the curve is the adaptation to exercise. When you start working out, your hemoglobin is ready to immediately unload more oxygen. Make sense? Does it make sense? Okay. Now, another important feature. Look at this. Think of a single, let's operate on the very reductionist terms. Think of a single hemoglobin molecule, okay? In the lungs, it becomes fully saturated. We're good? In the tissues, it's saturated by 3/4, 75%. Here. Does that make sense? And then the 75% of saturated hemoglobin goes back into the lungs. Are you with me?
I don't understand the tissues.
So, again, lungs, in the lungs, hemoglobin becomes 100% saturated. From the lungs, it goes into the tissues. In the tissues, it dumps 1/4 of the load for the tissues. Tissues use this oxygen. It's still 75% saturated. It goes back into the lungs for a full saturation again. Does that make sense to you? Are we clear? And it will circle around every time, dropping only 1/4 of the total load. That make sense? Imagine that a patient stops breathing, which means when you stop breathing, you still have a pretty considerable amount of oxygen bound to hemoglobin. Does that make sense? And basically, as long as your blood circulates, this hemoglobin will keep unloading into the tissues. So in other words, having this 75% of oxygen, 75% saturation of hemoglobin, having this 3 oxygen molecules per 1 molecule of hemoglobin constantly bound to it, gives you some kind of a savings account depot of oxygen. If you stop breathing, you still have some oxygen to deliver to tissues. Does that make sense? It's enough for about a minute. Okay, then problems start. Are we clear? Now, how does this curve change if temperature increases or tissues become more acidic? So I found for myself that it's probably easier to explain it from qualitative physiological standpoint. So imagine that you have metabolically active tissue here. Compare metabolically active tissue to regular one. Which one has the lower oxygen concentration? Metabolically active, right? That makes sense? Now, oxygen is used to oxidize glucose, which produces CO2. If you have more oxygen to oxidize more glucose, how would it be reflected in the CO2 concentration? If you oxidize more glucose, you will produce more CO2. And more CO2 always means that pH of the tissue will go down. It will become more acidic. Does that make sense? So essentially, and on top of that, metabolically active tissues, they have higher temperature. Does that make sense? Because they actively metabolize, they produce heat. Good so far? So, now a question like conceptual, philosophical question, so to say. Metabolically active tissues, do they need more oxygen or less? They metabolically, not they have. Okay, when you have less money, do you need more?
Yes.
Yes. Like if you spend money, you need to get more money. So metabolically active tissues, since they spend so much oxygen, they constantly need more oxygen. Does that make sense? In any of these conditions, decreased pH, increased CO2, or increased temperature, the curve shifts to the right. Okay, so what does that mean? Let's take one particular instance with the temperature. Imagine that you have a fever, okay? And your body temperature is not 37, but now it's 39. We good so far? So what does that mean? It means that if previously you had 25% being unloaded at this partial pressure, now you're going to have, I don't know, whatever, 70%. I don't remember the actual numbers. You see what I'm saying? So it basically means that when your tissues are acidic or really warm or have high concentration of CO2, the amount of oxygen that is being unloaded in those tissues substantially increases. Okay, does that make sense? So this whole process, this whole thing is called Bohr effect. We're good so far?
Is it just the ones that you put in like a box?
Huh?
Is it just the ones you put in
Yeah,
a box?
so elevated CO2, decreased pH, and elevated temperature all increase the unloading of hemoglobin. And the curve shifts to the right. Does that make sense? Okay, so okay, that's good. That's good. Yeah, last couple of things that I wanted to mention in the relation to this conversation. First of all, listen. Know the following terms. I'm going to just put them. Know types of hypoxia. So I have a list. Huh? There's a list like ischemic hypoxia, when blood does not reach the tissue because there's blockage. You with me? Or histotoxic hypoxia, when tissues cannot use oxygen because of certain poisons. Or anemic hypoxia, when there is not enough hemoglobin in the red blood cells. Okay, or hypoxemic hypoxia, when somebody is being suffocated, when people cannot breathe physically. So just know the definitions. And one more thing that I wanted to mention, just to kind of give you an illustration. Have you heard about carbon monoxide? Good? Now look. Carbon monoxide, CO, can bind to the same iron, okay? Which results in the formation of carboxyhemoglobin, okay? We good so far?
Is it all of them?
Say it again?
Is it all of them or just one?
Oh, wait a minute. I'm going to explain. So, essentially, carbon monoxide and oxygen, they compete for these binding sites. For all of them, of course. There's no, look, you think about these four as being different. They aren't. These molecules, they're not humans, you know? They can distinguish. It's just a side. Okay, we're good? The problem is that carbon monoxide binds to this iron much stronger than oxygen. So in carbon monoxide poisoning, this is what happens. People inhale carbon monoxide, which is colorless gas. Carbon monoxide binds to iron, and oxygen simply cannot kick it out. And when carbon monoxide binds to the iron, oxygen can't bind to it anymore. Does that make sense? So all four seats are already occupied. Does that make sense? So the treatment for carbon monoxide poisoning is to take person into the fresh air, give them oxygen, as much oxygen as possible. So oxygen will replace carbon monoxide because of the sheer number, right? Does that make sense? And the sign of carbon monoxide poisoning is very red cheeks and arm and hands, because turns out that the complex of carbon monoxide with hemoglobin is cherry red in color. You see what I'm saying? So people who have carbon monoxide poisoning, they're not like white, pale. No, they bright red. Okay? Does that make sense?
Is the only way to get rid of it is by like hooking them up to oxygen because
Yep.
they can't do it itself?
Yep. Yep, that's all. They have to. So essentially, and remember, any poisoning, it's not yes-no situation. You can have, like, God forbid there is a fire and you get some carbon monoxide poisoning. It will be harder for you to breathe initially. And it will become progressively harder and harder until you can't. And again, you can breathe. The problem is when all hemoglobin is occupied by carbon monoxide, there are no spots to deliver oxygen from lungs into the tissue. Does that make sense? You can't do transport. Are we clear?